Okay, so we have the normal model. It's defined, we define whatever x is, and we say it's normal, approximately normally distributed with a mean, a given mean, and a standard deviation of sigma. So these other ones, two of these, the binomial and the geometric, are based on Bernoulli trials. Bernoulli was that guy whose picture was in the book. Okay, Bernoulli trials. Bernoulli trials have three important characteristics. Okay, so here are the characteristics of Bernoulli trials. There are only two possible outcomes. So if you're going to do a Bernoulli trial, there are only two things that can happen, success or failure. Okay, so if I flip a coin, that's a really easy one to see that there's success. If I flip a coin and I'm looking for heads, heads is a success, tails is a failure. There's only two outcomes when you flip a coin, right? Okay, now things like rolling a die can only have two outcomes. If you look at maybe rolling a 4 as being success and not a 4 as being a failure. Okay, answering a multiple choice test, you either answer correctly or incorrectly. So there are more than just, some people say, well, there's only two outcomes, so I can only use things that don't have two outcomes, like flipping a coin or yes and no or true and false. No, you can have things that have more outcomes than that if you look at it as success and failure, correct, incorrect, getting a 4, not getting a 4. So two possible outcomes will make a Bernoulli trial. Okay, the probability of success is the same on every trial. So like if I roll a die, what's the probability of getting a 4? 1/6. What's the probability of getting a 4 the next time I roll the die? It's still 1/6. It's always 1/6. The probability of getting a 4 is always 1/6. Okay, what's the probability if I have a multiple choice test, if I'm guessing on the answers, and each question has 4 options, what's the probability that I guess correctly? 1 in 4. And isn't that the same for every single multiple choice question? Okay, so probability of success is the same on every trial. I'm just trying to give you examples of things that can be Bernoulli trials. Okay, so the trials are independent. Well, independent means the next time you do something, like you answer on the first question, you guess B. Okay, the second question you go to, is that how you answer that? Is that affected by what you put on the first? It shouldn't be. It shouldn't be. But technically, if you think about it, you know, if you've answered too many B's, what are you going to tend to do? Not pick a B. Okay, but we assume they're independent. You make them not independent. You know, you make them dependent by your thought process, but truly they are independent of each other. Just like flipping a coin, rolling a die. If you do it multiple times, then they're not affected by what happened previous. The things that would not be Bernoulli trials would be like just drawing cards from a deck and not putting them back. Now you could put them back each time, and then that you could make it Bernoulli trials. So those are the three things that need to happen to make it Bernoulli trials. So some examples of Bernoulli trials: toss a coin. You've got heads or tails. Roll a die. Look at getting roll a 3 or not a 3, just as an example. So success, failure. You get a 3, that's success. Not a 3, that's a failure. Guessing on a multiple choice question. Or quiz. All right, so those are just some basic examples of Bernoulli trials. Okay, now that's Bernoulli trials. Okay, today's notes and the next day's notes are dealing with probability models that involve Bernoulli trials. So today's probability model that involves Bernoulli trials is called a geometric model. Okay, the geometric model tells us the probability that it takes a specific number of Bernoulli trials to achieve a success. We've actually had questions like this before when we did the basic probabilities back in chapters 11, 14, and 15. It asked the question, how long until I get a success? How many times am I going to have to toss this coin until I get a heads? How many times do I need to toss this coin to get tails? How many times do I need to roll this die to get a 4? How many times do I need to guess on a multiple choice question to get it correct? So what we're doing is we're doing the same event over and over again until we get a success. That's the geometric model. Okay? So x, the geometric random variable, is always x, and it's equal to the number of trials to get one success. The number of times I have to do this to get a success. Whatever you clarify as your success. You define your own success, or the problem defines the success for you. So the model is completely determined by one parameter p. So I want to clarify this. I want you to understand what the parameter is. And I'm going to do this by writing the normal model. The normal model has two parameters. Normal model has two parameters. They are mu and sigma. Okay? The parameters, the things that define or allow you to draw the picture of the normal model, are the mean and the standard deviation. If you know the mean and standard deviation, can you draw the whole normal model? Put it on the x-axis, put all the standard deviation. Yes, you can. The whole model is determined by that. Okay? Now, we don't draw pictures of the geometric model, but we determine the whole geometric model by just the parameter p. And p is the probabilities of success. Probability of success. So the one parameter that determines the geometric model is p. It's the probability. P is the probability of success. Okay, so on the multiple choice question, four answer choices, what is the probability of guessing that correctly? 1 in 4. Okay, you have A, B, C, or D. You're going to guess. What's the probability you guess correctly? 1/4. So if you're guessing on multiple choice questions, P is 1/4. If you're rolling a die and you're saying, what's the probability? The success is rolling a 2. What's the probability of success? 1/6. If you're tossing a coin and success is heads, 1/2. Okay, so a geometric model, the way you write a geometric model, x is approximately geometric, and the probability of success is p. So you always define your model by writing what x equals, and then you define that x is geometric and whatever the probability of success is. So for example, suppose I'm rolling a die until I get a 5. Okay, so x is roll a die until I get a 5. Well, is this geometric? Yeah, because geometric, the number of trials to get one success. I'm going to keep rolling until I get a 5. 5 is the success. So 5 is the success. 5 is a success. What's the probability of getting a 5? 1/6. So the probability of getting a 5 is 1/6. So that means I have a geometric model. X is approximately geometric, and the one parameter that determines that is p, which is 1/6. So this is how I write the geometric model for that problem. X is geometric, and the probability of success is 1/6. Okay, so further we can go up here and say, well, there's only two possible outcomes. Two outcomes. 5 and not 5. Probability of getting a 5 is always 1/6. And we know rolling a die is independent each time. So we want to answer the questions down here about this geometric model that we just defined up above. So what is the probability that I get a 5 on my first roll? It's 1/6. Okay, the probability that I get a 5 on first roll, well, that's 1/6. Because I got the 5, and that probability was 1/6. Okay, what's the probability I get my first 5 on my second roll? Okay, well, let's take a look. We have to look at each roll separately, don't we? Each roll. So the first roll, what do I get?
5. Not a 5.
I did not a 5. So so this is not a 5, and then this is a 5. So what's the probability that I get not a 5? 5 over 6 times 1/6. Okay, third roll. So how many blanks do I need now? 3. I need 3 blanks. I have to look at all 3 rolls separately. So what am I going to get on my first roll? Not a 5. And on my second roll? Not a 5. And on my third roll? I'm going to get a 5. See how I plan the problem out a little bit instead of just writing some numbers down? I'm planning it out. Planning my probability problem. I have 3 rolls. I'm going to get my first 5 on the third roll. So I know that first I don't get a 5. So what's the probability that I get 5 out of 6? Times 5 out of 6 times 1 out of 6. It's always the last one you do that you get the success in a geometric model. The last one you do is where you get the success. That's where you get that probability that you defined up in the beginning. Okay, so what is the probability I get my first 5 on the kth roll? Now, these make sense, and then all of a sudden you put kth in there and people are like, whoa, my head's spinning, I don't understand that. Kth just means like 7th, 12th, 15th, some other roll above the third roll. Okay, in other words, they're asking for in general, on any roll, let's say I said, what's the probability that I get a 5 on the 15th roll? How would you figure that out? Well, you know, the kth roll, any given roll, how many times are you going to multiply the not probability? 1 minus the total. So you're going to take 5 over 6 to not the kth power, but to the what power? K minus 1 power. Okay, if it were the 15th, if it were the 15th, you'd have 14 of them that were not 5s. And then the 15th one would be a 5. So 15, if K is 15, you take the not probability, this is the not probability, to the K minus 1, to the 14th power, and then you take the probability, P, to the, just times that first power, okay? It's the last one. The last one is where you get the success. All right. So, turn the page. So, at the top of the page, all we did was basically develop that formula. We just basically developed that formula. So for geometric models in general, any geometric model, okay, where X is the number of trials required to get one success, and that always happens on the last one, okay? The probability that X equals X, now that might seem confusing. The probability that X equals X, well, the probability that X equals 2 or X equals 3, however many trials we're going to do until we get a success, okay, is Q. Now Q, okay, we got to talk about what Q is. It defines Q. Q is 1 minus P. Okay, well, what was P? Okay, so X was a geometric model determined strictly by P. P is the probability of success. P is probability of success. Okay, we just talked about this on the previous page, but it probably hasn't had time to sink in completely. Rewrite it all here. Let it sink in. Okay, then when you go to read the book, you're going to be like, oh yeah, I remember reading that. I remember us talking about that. The more times you put things in your brain, the more chances you have to memorize it. Okay, so P is the probability of success. So Q is basically probability of failure, right? Q is like saying failure. All right, so you're going to take the failure to the X minus 1 power. Well, isn't that what we said over here on this page? Didn't we say K minus 1 power? We're just using a different number, X. X is how many times we're going to do it until we get a success. Okay, so the formula, the way you calculate, this is the formula for calculating